Hello friends, Agrawal US, Assistant Professor in Civil Department, Sandipani Technical Campus, Latur. Today's topic is conjugate beam and example here. Learning outcomes: after watching this video, student will be able to understand the concept of conjugate beam method, and also student will be able to calculate the slope and deflection by conjugate beam method. Now the theorems here. The first theorem is the shear at any point on conjugate beam is equal, that is in sign and value, to the slope at corresponding point on the real beam. And theorem second, the moment at any point on the conjugate beam is equal, that is in sign and value, to the deflection at the corresponding point on the real beam. Now some are the steps here. So determine the first is to determine the bending moment diagram for real beam. Then to set up an additional beam, that is called as a conjugate beam, having the span is equal to the real beam. Then to apply M by EI loading on the conjugate beam. Then next is to determine the reactions of conjugate beam. Then to determine shear force in conjugate beam where the slope is required in a real beam. And last one is to determine bending moment in a conjugate beam where the deflection is required in a real beam. Some sign conventions are here. The sagging bending moment for real beam gives the positive M by EI diagram, and hogging bending moment for real beam gives the negative M by EI diagram. The positive M by EI diagram means upward loading for the conjugate beam, and negative M by EI diagram means downward loading for the conjugate beam. The next is positive shear for conjugate beams mean anti-clockwise rotation of a tangent drawn to elastic curve with respect to original position at corresponding point in a real beam and vice versa. And last one is a positive bending moment for a conjugate beam means upward deflection of a corresponding point in a real beam and vice versa. So now here we take the example. Suppose this is hinge support and this is the roller support, and this point load is acting at a distance 2 meter, and next one is the 4 meter. This load is 60 kilonewton. This is A and this is the B. Here find slope at A and deflection maximum. Now EI is the constant. So now first we draw the BMD for this. So we know BMD for this is WAB by L here. This W is a 60 into 2 into 4 divided by the 6. So 10 into 2, 20 into 4 is a 80. Now this divided by the EI, so this becomes the M by EI diagram now. This diagram is positive. So now we have to draw the conjugate beam here of a same length. Now in the conjugate beam, make this hinge as a hinge. So no need to change of the support. This is roller support, so make it as roller support. Now apply this positive load on this beam. So we change here. See. Now we are seeing in the sign conventions, if the bending moment is the positive, so this loading is the upward. So this loading is the upward. And this is the AT by EI. So now here this is A and this is the B. So we know this loading is upward, so these reactions are the downward. So this is RA and this is the RB. So now first we find the reactions. So we are taking sigma MA is equal to 0 in the conjugate beam. Sigma MA is equal to 0 in the conjugate beam here. So now if we make the two part, suppose this is the first and suppose this is the second part. So now this create the anti-clockwise movement, so that is a minus. So 1/2 this base is a 2 meter and this base is a 4 meter. So this first part, so 1/2 base into the height into CG of this triangle. This is the x1 bar suppose. So this is the 2/3 of the 2. Then this second part here, this one, that again the minus. So 1/2 base is a 4 and height is a 80 by EI. Now CG of this is from here x2 bar suppose somewhere here. So this is 2 plus 1/3 of this 4. So 2 plus 1/3 of this 4. Then this RB is a clockwise, so plus the 6 into RB is equal to 0. So we got here the RB is equal to 106.67 divided by the EI. Divided by EI. This is a kilonewton meter square. Now this we assume the downwards, this answer is positive, it means this is a downward. Then apply the sigma Fy condition here. So this we are considering sigma Fy is equal to 0. So vertically upward is a plus and vertically downward is the minus. So this RA is a minus, so minus RA. Then this total load is upward, so plus that load is 1/2. Total base is a 6 into height is 80 by EI. Then again this reaction is downwards, that is minus, and the reaction is a 106.67 divided by EI is equal to 0. So here we got the RA is equal to 133.33 divided by EI kilonewton meter square. Again this is downward, this answer is positive, so we can say that it is 133.33 by EI and this is 106.67 divided by the EI. Now next is we have to find the slope. So slope at A. Slope at A means at here. So here this slope at A means at here slope. So we can say that slope at support A is equal to the shear force at A in conjugate beam. So that is equal to here. So we know here from the left side this slope is a downward, so that is a minus. So we can say that slope at A, that is a theta A, is equal to the minus the RA. So theta A is equal to minus 13. This RA is a 133.33. divided by EI. So as per our sign convention, this theta A is equal to, if the slope is negative, it means is clockwise. So we can say that 133.33 divided by EI, and that slope is a clockwise. So we got here the theta A. The next is to find the maximum deflection. To find the maximum, next part is the maximum deflection. So here we know, from this point we can say that this maximum deflection, suppose this point is a C. So this maximum deflection is occur between this BC section. So we are assuming that the maximum deflection occur in section BC. Now we know that in the case of the real beam, the maximum deflection occurs where the slope is 0. In real beam, maximum deflection occur where slope is 0. So in conjugate beam, so this maximum deflection occur at shear force is 0, because slope is a shear force in the conjugate beam. So shear force is 0. So we can say that here we are assuming this BC where the shear force is 0. So now here we draw the three-body diagram of this, or separate diagram here. This is 106.67 divided by EI. We know this height is 80 by EI, and this loading is upward, and this span is 4 meter. So we have to find the shear force anywhere the X, anywhere the X. So we have to make a shear force is equal to 0, because shear force is represents slope is 0 in the real beam. In the conjugate beam, shear force, so slope is replaced by the shear force in the conjugate beam. So we have to make a shear force at any distance x between this B and C is equal to 0. So here this height is suppose is y at a distance x. So we can say that is 80 by EI is total divided by 4. This 80 by EI divided by 4 is equal to the this y divided by the x. So this y is equal to the 20x. So we got here the location. We got here the height, this y, not location here, this height y. Now we have to make the shear force at this x is equal to 0. So here at section this, so from right side we know the shear force is positive, upward is positive, negative, it is minus. Here this triangle, 1/2 base is x into height is 20x by EI. 20x by the EI. Then from the right side, this downward force is the positive, so this is the plus 106.67 divided by EI is equal to 0. This is the shear force at any distance x is from the right side. This is a triangle. This is the force 1/2 base into height into plus the shear force, that is the reactions. So we can say that here this is the 10. So 10 x square by EI is equal to 106.67 divided by EI. So we can see that here this EI gets the cancel out. So here this x is equal to the 3.27 meter. Now this total length is a 4 meter. This total length is a 4 meter and this x is a 3.27, meaning our assumption is correct. So our assumption is correct. So we have to find out the maximum deflection at a distance 3.27 from the right support. So here now suppose this is a total beam. This is reaction 106.67 divided by EI is 133.33 divided by EI and this is our loading. So this is the 80 by EI. So maximum deflection at the 3.27 meter, that is equal to, now here suppose this distance is this 3.27 meter. So for that deflection we have to take the moment at this 3.27. So that is equal to here 1/2. So this force create the second bending moment. This is plus 1/2 base is 3.27 into here we have to find the height here y. So this y is equal to here is 80 by EI divided by 4 is equal to this y divided by the 3.27. So this y is becomes the 65.4 divided by EI. So here we got the value of y is 65.4. So 1/2 base into height is 65.4 divided by EI. Now into from here distance is x bar, that is a 1/3. So 1/3 of 3.27 and this create the hogging bending moment, so that is minus 106.67 divided by EI into 3.27. So that is maximum deflection, that is equal to, this value is minus 232.25 divided by EI. Now in case of this deflection, if this bending, this is the bending moment, so that is equal to the maximum deflection. This maximum deflection at 3.27 meter, that is equal to the bending moment at 3.27 meter. So when this moment bending moment is minus, so we can say that that is the downward deflection. So that is equal to 232.25 divided by EI it is a kilonewton, this meter cube, and this is the downward. So this is the maximum deflection. So this is our final answer. And previous one again is this one is our deflection. This theta is the slope at A, and this is the maximum deflection. Thank you.